Hi everyone, in this video I am going to demonstrate how to build molecular clusters using newly introduced EPIC algorithm in DAMQT version 3. I am Anmol Kumar, one of the contributors of this program. There are a lot of additions made to this third version of DAMQT, one of which is the ability to build and optimize large molecular clusters which mainly interact non-covalently with each other, like the famous water clusters or carbon dioxide clusters or zinc oxide clusters. Such molecular clusters are studied experimentally for their size-dependent physicochemical properties. You can also optimize and analyze biologically relevant systems like DNA base pair interactions. Quantum chemical optimization of such large non-covalently interacting systems becomes a daunting problem, mainly because of the poor convergence and large number of local minima. And if you are using post-Hartree-Fock method, then the computation is very time consuming and often ends up unconverged. EPIC algorithm, which was originally designed back in 90s by Professor Sridhar Gadre and co-workers, is based on very simple idea of using QM derived electrostatic potential of the host molecule for optimizing the position and orientation of any molecule which is interacting with the host. This simple algorithm along with the capabilities of DAMQT can prove really helpful to researchers dealing with such systems. So without further ado, let us now get started with the demo. For the purpose of demonstration, I am going to create molecular dimer of chloromethane. For adding a monomer to a host molecular system, you need to have an output from LCAO calculation containing the density with spherical basis functions for the host molecule. For example, I have a formatted checkpoint file of chloromethane from the Gaussian software here, which means that I will be able to evaluate the electrostatic potential anywhere in the space because of this molecule. In this EPIC model, we make use of electrostatic potential of the host at the atomic position of the guest molecule, which should have the atomic charge information. Now the intention here is to optimize a chloromethane molecule bearing only partial atomic charges in the presence of electrostatic potential of this chloromethane molecule for which we have the formatted checkpoint file. So let us go ahead and launch DAMQT from the command line. Here you can choose the language of the program between English and Espanol. You now need to hit the start. This is the graphical user interface of DAMQT. On the left, you see various different options that allows you to perform different types of topological analysis of electron density and electrostatic potential. In the middle, you will see the log output of any operation that you perform on the left side. On the right hand side, you see 2D viewer, which allows you to display 2D plots or contours. And this is the 3D viewer, which allows you to display, build and modify the molecules and their assembly. The EPIC algorithm can be accessed inside the 3D viewer. So you can see we have EPIC algorithm over here. And this is the canvas. We will talk about this later. The EPIC algorithm is placed as an option inside the 3D viewer, so you can optimize the molecule that you see on the display canvas. We first need to initialize the project and extract the relevant information from the FCHK file of the host molecule. Once you load the FCHK file, the working directory will be automatically filled, which is the base directory containing the formatted checkpoint file. You then need to hit the execute button, and you will find various information extracted from the FCHK file in this text display, such as number of electrons, number of basis functions, number of molecular orbitals. If you check in your directory, you will now see new files created in your directory. The DAMProj file contains all the default inputs to DAMQT initialization. The .den file contains the density information. And depending on whether you used Slater or Gaussian orbitals, you will find the basis set information in the SGBS or GGBS file. GA ORBA file contains molecular orbitals for 2D and 3D display. At this point, also perform atomic density operation, which is basically partitioning the molecular electron density into atomic fragments from the output files that are extracted from the FCHK file. Increase the number of spherical harmonics, that is L value, to 15 for sufficient accuracy of the later evaluation. You may choose to use more than one processor for this job if the parallel version is installed. Let me use 2 processors here and hit execute. This will take a while and you will see the output displayed once the job is done. If you go back to your directory, you will see new files created. DAMQT 320 input contains the DAMQT input file for creating the atomic densities. The values inside this file is manipulated by the choices that you entered in the GUI. You will also see XYZ file containing the coordinates of the molecule in angstrom. More importantly, you will see DAMQT and DMQT files containing the atomic fragment density information, and they will be used for all following density and potential evaluation. The multmod file contains modules for atomic multipolar moments. We are now ready to build the cluster, or the dimer in this case, using the electrostatic potential of our host molecule. Open the 3D viewer. You will see the canvas on the right, and you will see the options of adding the molecule. So let us go ahead and load the host molecule first. As you can see, the molecular coordinates are now extracted in XYZ format that you can use for displaying the molecule. Now the next step is to add the guest molecule near the host, which in our case is the same molecule because we want to create a dimer of chloromethane. So click on the add molecule and you can choose the same file as before. And internally it will be treated as your guest molecule. If you were to add another molecular system, you need to have the coordinates of the molecular system in XYZ format, preferably in your working directory. Right now you can see both molecules are on top of each other and both are active. Uncheck the first molecule so it remains unchanged in its position. Now only the second molecule is active. Now press the shift button and hold the right click on the mouse and drag the guest molecule away from the host. You can also hold left click to rotate the molecule. You can place the guest molecule in an orientation that you think is favorable. Now you can make a better decision of placing the guest molecule near the host if you have topological information of the electrostatic potential of the host molecule. For this purpose, you need to go back and calculate the critical points of the electrostatic potential of the host molecule. Let us do this step, and let me remind you that this step is optional here. For evaluating the critical points, you need to click on the molecular topography and choose molecular electrostatic potential. Choose the highest L value to be 15. Use more than one processor here and hit execute. It will take few seconds to obtain the critical points of the molecule, and the timing depends on the size of your system and the number of processors that you are utilizing for the job. Once you have the critical points, you can see the log file is here. All the description of critical points are over here. Once you have the critical points, you can load the critical point on top of the host molecule. Go to edit, click on critical points, choose the critical point file. You can now see a CPS V file containing the critical point of electrostatic potential. As you can see, the critical points are now displayed over here along with the host molecule. The red color critical points show the most negative minimum in the electrostatic potential of the host molecule, and you should now place the atom of the guest molecule that bear the positive charge near the electrostatic potential minimum. So basically, critical points are assisting the placement of the guest molecule. For example, I have placed the hydrogen of the guest chloromethane near the negative valued critical point of the host chloromethane. Let us now go to Optimize Cluster tab, which performs the EPIC optimization of host and the guest. As you can see, all the output files will be put in this directory, and there is a default name for the prefix of the output files, which is cluster here. You can change this as you wish. Let me change this to CH3Cl dimer. Now remember, you added 2 molecules in the add molecule section. By default, the first one is taken as the host. Just to remind you that the host must have the associated DAMQT and DMQT files in the working directory. So you can choose the guest from the canvas There is another option here which allows the guest molecule as the template file and lets the program decide its placement and how many of them you want to optimize at once. This option necessarily requires critical point information of the host. As you can see, you have 3 red colored critical points where program can automatically place the guest molecule in appropriate orientation. You may choose one or all 3 critical points for placing the guest molecule. So for example, I am going to choose only selected critical points for placing the guest molecule. For this, I need to go to edit the host molecule, go to critical point section, choose CP symbols, choose only selected critical points. You can double click on any of the critical points to choose them. I am choosing one of the critical point over here. Here you need to give the information whether the first one is the host or the second one is the guest. The guest information that is provided over here will be used as template, meaning that the coordinates of the guest molecule will be used to place them on the chosen critical point. If you don't click on this option, only selected critical points, the program will place only one guest molecule at the most negative minimum. So for now, I am not going to choose my guest entry as template. Let's say that I am satisfied with the placement of the guest molecule as on the canvas. So I click on choose guest from canvas. You might be wondering that we never talked about obtaining the partial charges of the guest molecule, which is required to evaluate the electrostatic interaction energy. DAMQT provides 2 easy options. One is to supply the charges externally from a file that contains a column of atom names exactly same as the guest molecule, and the second column should contain the partial charges. If, for example, you are building a homodimer, then you can extract the charges from the multmode file of the host molecule and use it as partial charges of the guest molecule, which is what I am doing here. You can see the extracted charges in edit, and you can also edit these charges. Another option is to use OpenBabel software, which is a free toolbox for interconverting the chemical file formats and can be easily installed on any operating system. OpenBabel can also assign partial charges very quickly, and you have various different options of charge models to choose from. Let me choose Qt Pi model for assigning the charges because it works really well for the EPIC optimization. Here you can change the default options of optimization before running the optimization. I will leave them as default. Now hit the execute button. While the calculation is running, you can see that the execute is inactive, and it will become active only after the calculation is complete. Once the EPIC optimization is done, you may choose to optimize it further using QM engine. DAMQT makes it easier to create the required QM input file for this EPIC optimized dimer. And you can also run the calculations locally or remotely depending on the availability of the QM engine. For this, hit the quantum mechanics button and a new window will pop up with options of creating the QM input file. You can also launch this window from the menu bar of the main window. But when you launch it from the EPIC optimizer window, you will see that the dimer coordinates are already loaded over here. You can give it a title. All the common QM engines are taken care of. Here you have Gaussian, Games, MolPro, Mopac, NWChem, and Cypher. The input file format in the preview changes based on the choice of the QM engine. Let me use Cypher here because that is locally installed. You may choose to do energy calculation, geometry optimization, frequencies, or you can also do optimization plus frequencies and NMR calculation. Here let us do geometry optimization. You can choose various level of theories here. You can also enter a new level of theory if you want. You can choose different spin states, total charge of the molecule, and multiplicity. You can choose between various basis sets that are available here, and you can also edit and enter a new basis set. Let us choose STO3G for faster calculation. You can enter your own additional keywords over here if the options are not available in the drop-down menus. The default keywords 5D7F ensures that the spherical basis functions are used in the FCHK file. You can run locally and also remotely. In remotely, we support 3 different job schedulers, PBS, SGE and Slurm, for which we can create the job scripts. Let me run locally here. I am going to use more number of processors. I can also enter a memory, but I am going to use the default. The time limit option is to run remotely for a certain period of time. This is my working directory. This is the name of the input file. And here is the execute command. So it is going to run psi4 followed by my input file name. If I am not satisfied with the input file here, I can edit it further and save. Let us now submit the calculation. You will see that the submit will remain inactive till the optimization is complete. It will take a while for this calculation to be finished. While the QM calculation is running, you may be interested in looking at the trajectory of EPIC optimization. For this, you need to go and load the xyz_frames file in the animation section. Choose the speed of the animation. You can also choose to record the animation and click on replay. This is the final optimized geometry. If you go back to your directory, you should see a new MP4 file which is created, which is the movie. Let me play this movie for you. As you can see, the computation has ended. If you go back to your directory, you will see new files created. You will see the input.dat file, which is the output file of psi4. You can go to the end of the file and you can see that the computation is normally terminated. You will also see the formatted checkpoint file of the dimer, so you can use this to grow the cluster further. Let us now look at the QM optimized dimer in the screen. For this, you need to delete the EPIC optimized dimer over here. We need to go back to project and load a new project. This time we will load the chloromethane dimer FCHK file instead of the monomer. We can go and hit execute, and as you can see, now the information is extracted for the dimer. Go back to the display and add the QM optimized dimer geometry, which is the chloromethane dimer GGBS file. Also load the EPIC optimized cluster. Hide the host and the guest. As you can see, if I superimpose, the EPIC optimized geometry and the QM optimized geometry resemble each other very well. This shows the importance of the EPIC algorithm, which will give you a reasonable geometry to start with, which you can use to optimize the cluster further using quantum mechanical operations. Having a good initial geometry helps you to minimize the time which is required for QM calculation. Hope you have found this video helpful and use EPIC algorithm for optimizing the molecular clusters for your research. Thank you.